Alright, welcome back. We're doing another example here on nodal analysis, and in this case we have two voltage sources. We have a 3 volt and a 2 volt voltage source, and a couple different resistors that are in no particular order. So to solve this problem we're going to use nodal analysis, and to get started with that, first we have to identify a ground. In the case where there's voltage sources, especially if two voltage sources are connected to the same node, you're probably going to want to ground that node because it'll reduce the number of unknowns that we have. So let's pick this one. Let's draw on a ground, and this is going to serve to be our 0 volts reference point for the rest of the circuit. But because we have voltage sources attached to it, that means that across this element, it's basically this node here is going to be 3 volts higher than the 0 ground. And then same thing when we cross this voltage source, it's going to jump by 2 volts. So this node up here is going to be equal to 2 volts higher than ground. Then when we look at this, we only have two remaining unknown node voltages, this one and this one. So let's give them names. Let's call the voltage of this node, let's call it VA, and let's call the voltage of this node VB. Now when we're doing nodal analysis, basically all we do is Kirchhoffs current law at each of the nodes that have unknown voltages. So we have two, so we're going to need the current flowing into node A and out of node A and also B. So we just assume some directions here. It doesn't actually matter if we get them right or wrong. But let's just pick some for the purpose of this problem. So we'll call this I1. Let's call this one I2 going this way. And let's say we have I3 and then I4. And let's say I5. Cool. So we just need to write KCL for each of the nodes. So let's write it, let's do KCLA first. And you can either sum up, so all of the currents flowing in are on one side of the equation and all of the currents are flowing out on the other side of the equation, or if you prefer, you can pick a convention where we say like negative is the sign we assign to a current flowing in and positive for out. It means basically the same thing. It's just basically if we sum them up together that we get a net of 0. So let's go with that. Let's say that then because I1 is flowing in, we're going to have negative I1. And then we have I2 flowing out, so we have plus I2 and plus I3 is equal to 0. Clearly, if you just brought this I1 to the other side, you would have these two, which are the flows out, equal the flow in. And because Ohm's law is V equals IR, we can rearrange that for current, so we have I is equal to V over R. So even though these currents are unknown right now, we can write them in terms of the voltage drop across the element and the resistance. So for I1, let's keep the negative sign, and the current is equal to voltage over resistance. Now we've assumed that the current is going from left to right, which means it's flowing from a high voltage to a low voltage. So we're assuming that 3 volts is higher than VA. If it turns out that we got this wrong later in the problem, it's fine. We'll just find this current to be negative and we'll switch the direction. But we're going to proceed as we've drawn it. So the voltage across it is going to be 3 volts minus VA. So that's the difference. We subtract the smaller one from the bigger one, and that's based on the assumption that we've made. And then we just divide this by the resistance, which is 2 ohms. Okay, for I2, we have positive, and when we look at I2, that is this one right here. And so we're assuming the current to be going down, so which means we assume that VA is bigger than 0. So the voltage drop across that resistor is going to be VA minus 0 over the resistance, which is 3 ohms. And then for the other resistor where I3 is flowing through, the voltage drop here, again we're assuming it's flowing this way, so we assume VA is bigger than VB. So the difference, or the voltage drop across this resistor, is going to be VA minus VB. And it's over 4 ohms. Alright, let's give ourselves a bunch more space here to work with, and we'll just go through this, simplifying this calculation. So we're going to multiply each term here by the lowest common denominator, basically, which is 12. So we multiply by 12 to each term, and in this case we can simplify a little bit. So 12 divided by 2, we're left with a negative 6 here. 12 divided by 3, we're left with a 4, and 12 divided by 4, we're left with a 3. So we can just rewrite this a little bit. So we have negative 6 times, what I'm also going to do, actually I'm going to drop the units of volts and ohms because it gets a little bit confusing here when you have this unit of volts and then a V also in the name of the variable. So we're just going to say that this is 3 minus VA, and we've gotten rid of the ohms as well. So each term here is going to be in units of amps. Okay, so then the next term just becomes 4 VA, and the next term just becomes 3 times VA minus VB. So we can just distribute those out and simplify to get 13VA minus 3VB is equal to 18. Alright, so let's also write the expression for KCL at node B, and we need to scroll up here to just double check what the values actually were. So we have I4 flowing out, so let's give that a positive, and we subtract I3, which is coming in, and subtract I5, which is coming in, and set that equal to 0. Again, you could move these negatives to the other side and have everything flowing out equals everything flowing in if you prefer. But let's go through with the same logic as last time. So looking at this resistor for I4, we're going to replace I4 with this expression, which is the voltage drop divided by the resistance. And in this case, the voltage drop is VB minus 0. And again, because of the direction that we've picked, for the current, we're assuming that VB is greater than 0, so we subtract 0 from VB. And that's all over 2 ohms. And then for I3, we do the same thing. So the voltage drop, we're assuming the current is going left to right. So the voltage drop is going to be VA minus VB over the resistance, which is 4 ohms. And then we can do the same thing for the other one, for I5. And we're assuming the current is going from right to left. So we're going to say that the voltage drop is 2 volts minus VB all over the resistance, which is 1 ohm. And set that equal to 0. Alright, we can give ourselves more space again, and let's multiply everything by the lowest common denominator, which is 4 in this case. So we'll multiply every term to 4. You can even multiply the 4 to the 0, but it really doesn't matter because nothing will happen there. This 1 will disappear. This 4 and this 4 will disappear, so we'll be left with a negative 1 here, and this 4 will cancel with that, so we have a positive 2. So that leaves us with this first term is just 2VB, and then we have minus VA minus VB, and this is plus 4 times 2 times VB. Again, I'm just dropping the units of volts because it gets confusing here, and the units of ohms. If you want to carry it through, you might want to do a better job of distinguishing between when it's a unit and when it's a variable name, but I prefer just to drop them. So yeah, let's set that equal to 0. And we can just distribute out what we have left. And this just simplifies to VA equals 7VB minus 8. Alright, so we just want to take this VA and plug it in right here. So we get 13 times that whole expression, which is 7VB minus 8 minus 3VB is equal to 18. And then we can just simplify this a little bit, and we'll just get VB is equal to 122 over 88. And then we can just take this and just plug it right back into the other expression. So let's actually take the fraction because it's going to give us less rounding issues. But we have VA is just equal to 7 times 122 over 88 minus 8. And we find that VA is equal to 1.70 volts. So let's go and label these onto the original diagram then. So VA is equal to 1.7 and VB is equal to 1.39. That means we can find the voltage drop now across every resistor. So V1 here is just going to be 3 volts minus 1.7 volts, which gives us 1.3 volts. We can do the same thing here, 1.7 minus 0. That just gives us the voltage here of 1.7. The voltage drop across this resistor is 1.7 minus 1.39, which is V3, which is going to be 0.31 volts. The voltage drop across here is 1.39 minus 0, so that is just V4 is equal to 1.39 volts. And then the voltage drop from here, 2 volts minus 1.39, is just V5, which is equal to 0.61 volts. And then we can just really quickly calculate the current flowing through each resistor using the Ohm's law here, because current is again just equal to voltage divided by resistance, so we just take the voltage divided by the resistance for each one. So I1 is just going to be 1.3 divided by 2, which gives us a current of 0.65 amps. For I2 here, we just have 1.7 divided by 3 for 0.57 amps. For I3, 0.31 volts divided by 4 ohms, which gives us 0.08 amps. And then here, 1.39 volts divided by 2 gives us 0.7 amps. And then lastly for I5, 0.61 divided by 1 is just 0.61 amps. And then we can just check that the current flowing in equals the current flowing out, and 0.65 is equal to 0.57 plus 0.08. And then at this node, the current flowing out is 0.7, and the current flowing in is 0.61 plus 0.08, and that's just off by a tiny little bit for rounding, but basically we can see that Kirchhoffs' current law is satisfied for both of these nodes. And yeah, that's basically the problem. If you were asked to find also the power dissipation and stuff like that, you could do that, but you might just be asked to find the current flowing through each resistor, which we've done using nodal analysis in this example.